Welcome to this coding solution walkthrough. In this video, we'll explore LeetCode problem number 1666, change the root of a binary tree. This problem challenges us to restructure a binary tree so that a given node becomes the new root. It's a fascinating problem that touches on tree traversal and manipulation techniques. Let's dive in. In this problem, you are tasked with changing the root of a binary tree. You are given the current root of the tree and a specific node within the tree that you must make the new root. To achieve this, you will rearrange the tree in a specific way. The path leading from the original root to the given node will form the new right spine of the tree. This means that each parent node in this path becomes the right child of its child. Subtrees that are not part of this path should remain unchanged, and all left children along the path will be set to null. Ultimately, your goal is to return the new root of the binary tree after performing this transformation. The output of the function is simply the new root of the rearranged binary tree. To better understand how this works, let's look at an example. Suppose the input binary tree is represented as 1, 2, 3, 4, 5, null, null, and the node you want to make the root is 5. Before rearranging, the tree looks like this. The root 1 has 2 children, 2 on the left and 3 on the right. Node 2 further has 2 children, 4 on the left and 5 on the right. After rearranging to make 5 the root, the tree transforms into a linear structure. Node 5 becomes the new root, and the path from 1 to 5 forms the new right spine of the tree. The subtree containing 3 remains unchanged, as it is not part of the path. The rearranged tree in the example is represented as 5, null, 2, null, 1, null, 3. Here's how the transformation works. The path from the original root 1 to the new root 5 has been converted into the new right spine, with each parent becoming the right child of its child. All left children along this path have been set to null, and the subtree rooted at 3 remains intact since it was not part of the transformation path. This clearly demonstrates the rules of the problem, forming the right spine from the path and preserving any subtrees not in the path. Here's another example to illustrate the concept further. Suppose the input binary tree is represented as 1, 2, null, 3, null, 4, null, 5, and the node you want to make the root is 4. Before rearranging, the tree is a linear structure where each node has only a left child, with 1 as the root and 5 as the leaf node. After rearranging to make for the root, the tree is transformed into a right-leaning structure. Node 4 becomes the new root, and the path from 1 to 4 forms the new right spine. The subtree rooted at 5, which is not part of the path, remains unchanged. The output for this example is 4, null, 3, null, 2, null, 1, null, 5. To explain this transformation, the path from the original root 1 to the new root 4 has been converted into the new right spine of the tree. All left children along this path have been set to null. Meanwhile, the subtree rooted at 5 remains unchanged, as it is not part of the transformation path. This example highlights how the rules of the problem apply to trees where the path to the new root includes multiple levels. In the simplest case, consider a tree with only one node. If the input binary tree is 1, and the node you want to make the root is also 1, then no rearrangement is needed. The tree remains as it is, with 1 as the root. In this case, the output is simply 1. This covers the edge case of a single node tree, where the structure is already valid, and no changes are required. Finally, let's discuss some important constraints and edge cases to keep in mind. First, the number of nodes in the tree can go up to 10,000, so the solution must be efficient to handle large inputs. For balanced binary trees, it's crucial to ensure that subtrees not part of the transformation path remain unchanged. Additionally, in cases where the path includes all nodes, the final tree will become a linear chain. Understanding and accounting for these scenarios will help ensure that the solution is robust and adheres to the problem's requirements. To solve the problem of changing the root of a binary tree, the core idea is to restructure the tree so that a given target node becomes the new root. This requires reassigning the parent-child relationships along the path from the current root to the target node. One approach we can consider is the brute force traversal method. The intuition behind this approach is straightforward. We traverse the tree to locate the target node and determine the path leading to it. Once we have this path, we systematically reverse the parent-child relationships for each node along the way. For example, if a node was originally a child of its parent, it would now become the parent, and vice versa. This involves explicitly updating the pointers for the left and right children of each node to ensure the new tree structure is correctly formed. While simple in concept, this approach involves several manual steps that need to be carefully managed to achieve the desired result. When considering the brute force traversal approach, we need to evaluate its performance and practicality. The time complexity is O(n), because we must traverse the entire tree to locate the target node. The space complexity is O(h), where h represents the height of the tree, as we need to either store the path explicitly or use a recursive call stack proportional to the height. However, this approach has notable drawbacks. First, explicitly storing the path to the target node adds additional overhead and complexity. Second, updating the parent-child relationships manually can be error-prone, especially if the tree structure is more complex. This lack of systematic handling makes the brute force method harder to maintain and less efficient overall. An optimized alternative to brute force is the recursive rerouting approach. This method leverages recursion to reverse parent-child relationships directly during the traversal process, eliminating the need to explicitly store the path. The key idea is to recursively navigate down the tree until we reach the target node. Once we've arrived at the target, we propagate it upwards as the new route while systematically reversing the relationships during the return phase of the recursion. For instance, as we backtrack, the current node becomes the right child of its left child, and the left child becomes the new root. Additionally, the pointers of the current node are updated to prevent cycles in the tree. This approach is both systematic and clean, as the recursive structure aligns naturally with the hierarchical nature of the tree. The time complexity remains O(n), since we traverse the tree once, and the space complexity is O(h), due to the recursive stack. By eliminating explicit path storage and handling pointer updates systematically, this method offers a more elegant and reliable solution. While the recursive rerouting approach is elegant and efficient, it does come with a potential limitation. Specifically, the recursive stack usage can become problematic for very deep trees, as it may lead to stack overflow in cases where the tree is highly unbalanced. To address this limitation, an alternative approach is to use iterative simulation. By employing a stack or queue, we can simulate the recursion process iteratively, which avoids the risk of stack overflow. In this method, we traverse the tree iteratively to locate the target node while maintaining a reference to the parent of the current node. As we unwind the traversal, we reverse the parent-child relationships in a controlled manner, ensuring the tree structure is updated correctly. This approach has the same time complexity of O(n) and space complexity of O(h), but it provides more control over the traversal process, making it suitable for trees where recursion might fail. However, it introduces additional complexity due to manual management of the stack or queue. After evaluating the different approaches, the recursive rerouting method was chosen as the primary strategy for solving this problem. This approach is preferred because it naturally fits the structure of the problem, allowing us to reverse parent-child relationships during the return phase of recursion without needing explicit path storage. Its systematic and clean handling of pointer updates minimizes the risk of errors, and its time and space complexity are optimal for balanced trees. However, it's important to acknowledge the trade-offs. For extremely deep trees, recursion may lead to stack overflow, in which case the iterative simulation approach serves as a viable alternative. Despite this, for most practical scenarios, recursion is favored due to its simplicity, readability, and alignment with the hierarchical tree structure. By leveraging recursion, we achieve an efficient and elegant solution that balances performance with maintainability. The problem we're tackling is to restructure a binary tree so that a specified target node becomes the new root. This involves rerouting the parent-child relationships along the path from the current root to the target node. The challenge lies in ensuring that the tree remains structurally intact and all nodes remain connected properly throughout the process. To solve this, the algorithm begins by locating the path to the target node. This can be done using a depth-first search or breadth-first search traversal. While traversing, we maintain a parent map, which records the parent of each node. This map will be crucial for reversing the tree structure later. Once the target node is located, the next step is to reverse the path from the current root to the target. Starting at the target node, we work backward through the parent map, changing the parent-child relationships along the way. For each node, its parent becomes its child, and we update the left or right pointers accordingly. This process continues until we reach the original root, effectively reversing the path and establishing a new hierarchy in the tree. To ensure the entire tree remains valid during the restructuring, we must carefully handle subtrees at each step of the reversal. For any node on the path, its other subtree, the one not part of the reversed path, must remain attached and intact. For instance, if the node was a left child of its parent, its left subtree should remain unaffected. Similarly, if it was a right child, its right subtree must remain undisturbed. Once all parent-child relationships along the path are reversed, we set the target node as the new root of the tree. At this stage, the restructuring is complete. We should also handle edge cases, such as when the target node is already the root, in which case no changes are necessary. If the tree is empty, we simply return null. Finally, it's important to ensure that no cycles are introduced during the rerouting process, as this would break the tree structure and violate its properties. The algorithm relies on a few key insights: the use of a parent map for efficient traversal reversal, in-place updates to optimize space usage, and careful handling of subtrees to preserve the tree's integrity. To implement the algorithm, we rely on two primary data structures. First, the parent map, which is a dictionary that stores parent-child relationships during the initial traversal. This enables us to reverse the path efficiently without needing additional tree traversals. Second, we use either a stack or a queue to perform the traversal, depending on whether we're using depth-first search or breadth-first search. Now, looking at the complexity analysis, the time complexity of this algorithm is O(n), where n is the number of nodes in the tree. This is because we traverse the entire tree once to locate the target node and then reverse the path, both of which are linear operations. The space complexity is also O(n), accounting for the storage of the parent map and additional space used during traversal. To understand this better, let's consider an example. Suppose we have a binary tree where the root is 1, with children 2 and 3, and node 2 has further children 4 and 5. If the target node is 5, the goal is to make node 5 the new root while maintaining the tree structure. Let's break down the execution step by step. First, we construct the parent map by traversing the tree. The resulting map would look like this: node 2's parent is node 1, node 3's parent is also node 1, node 4's parent is node 2, and node 5's parent is node 2. With the parent map ready, we move on to reversing the path. Starting at node 5, we make its parent, node 2, a child of node 5. Then we move up to node 2, making its parent, node 1, a child of node 2. During this process, we carefully ensure that the left and right pointers are updated correctly to preserve subtrees. For instance, any subtrees of nodes 2 and 1 that are not part of the reversal path are left intact. Finally, we designate node 5 as the new root of the tree, completing the restructuring process. The updated tree now has node 5 as the root, node 2 as its left child, and node 1 as the left child of node 2. The tree remains fully connected and valid. The final tree representation reflects the successful restructuring. Node 5 is now the root of the tree, with all connections preserved and each subtree intact. The tree maintains its integrity, and no nodes are disconnected or lost during the process. This approach achieves the desired transformation efficiently, leveraging the parent map for traversal and in-place updates to minimize space usage. By carefully handling subtrees and edge cases, the algorithm ensures that the tree remains valid and no cycles are introduced. With node 5 as the new root, the binary tree is completely restructured, demonstrating the effectiveness of the algorithm. Here, we start by defining a node class to represent each node in the binary tree. Each node has a value, left and right child pointers, and a parent pointer to keep track of its parent node. This setup allows us to traverse both upwards and downwards in the tree. Next, in the solution class, we define the flip binary tree method, which takes two arguments: the current root of the tree and the leaf node that we want to make the new root. Inside this method, we initialize two variables: current, which starts at the given leaf node, and previous, which keeps track of the previously visited node during traversal and is initially set to none. The goal is to traverse from the given leaf node up to the original root, flipping the parent-child relationships along the way. To achieve this, we use a while loop that continues as long as current is not none. Within the loop, the first step is to store a reference to the parent of the current node in the next underscore node variable. This is necessary because we will modify the parent pointer of the current node shortly, and we need to avoid losing track of the original parent. Now, we rewire the current node by setting its parent pointer to the previous node, effectively reversing the parent-child relationship. If the current node's left or right child was previously pointing to previous, we disconnect it by setting it to none. This ensures that no dangling connections remain as we flip the tree. Next, we check the next underscore node, which represents the original parent of the current node. If the current node was the left child of next underscore node, we make this parent the new left child of the current node. Similarly, if the current node was the right child of next underscore node, we make it the new right child. This step completes the rewiring for the current node. Afterward, we move up the tree by updating previous to the current node and current to next underscore node. This way, we continue the rewiring process for the next node in the path toward the original root. Once the loop exits, all necessary connections have been flipped, and we return the original leaf node, which has now become the new root of the tree. Here, we start by defining a node class to represent each node in the binary tree. Each node has an integer value, references to its left and right child nodes, and a parent node. The constructor initializes these fields, setting the left, right, and parent pointers to null by default. Then, in the solution class, we define the method flipBinaryTree, which takes the root of the tree and a leaf node as input. The goal is to flip the tree so that the given leaf becomes the new root. Inside the method, we initialize two variables, current, starting at the leaf node, and previous, which begins as null. The while loop then traverses the tree from the leaf to the root, flipping connections as we go. At each step, we store the parent of the current node in the next variable. This allows us to rewire the parent-child relationships effectively as we proceed. Within the loop, the first step is to set the parent of the current node to previous, which begins the process of reversing the tree structure. Next, we handle the left and right child pointers of the current node. If the left child points to previous, it means we've already rewired this connection, so we set it to null. Similarly, if the right child points to previous, we set that to null as well. This ensures that the original parent-child links are broken. Then, we check the next node, which is the original parent of the current node. If the next node's left child is the current node, we reassign the current node's left pointer to next. Otherwise, if the next node's right child is the current node, we assign the current node's right pointer to next. This step effectively flips the direction of the parent-child relationship. Finally, we update previous to the current node, and current moves up to next, continuing the traversal toward the original root. Once the loop completes, we return the leaf node, which has now been transformed into the new root of the tree. To begin with, we're working with a simple linear tree where each node only has a left child. The input tree consists of 3 nodes, 1 is the root, 2 is its left child, and 3 is the left child of 2. Here, the goal is to make node 3 the new root of the tree. We initialize 2 variables, current, which starts at the leaf node, node 3, and previous, which is set to none initially to track the previous node during the reconfiguration. In the first iteration, current is node 3, and since it has a parent, node 2, we save this parent as next underscore node. Then, we sever the connection with its parent by setting current.parent to previous, which is currently none. We also remove any child references from node 3 by setting both node 3.left and node 3.right to none, ensuring it won't point to any old children. After removing the old child references, we rewire node 3 to point back to its parent, node 2, by assigning node 3.left to next underscore node. At this point, node 3 effectively becomes the parent of node 2. We then update the tracking variables, previous becomes node 3, and current moves to node 2 to continue the process. In the second iteration, current is now node 2, which has a parent, node 1. We save this parent as next underscore node and break its parent connection by setting node 2.parent to previous, which is now node 3. Node 2's old child references are cleared by setting node 2.left and node 2.right to none. Finally, we rewire node 2 to point to its parent, node 1, by assigning node 2.left to next underscore node. Once again, we update previous to node 2 and move current to node 1. In the third iteration, current is the original root, node 1, which no longer has a parent, current.parent is none. We save next underscore node as none since there are no more nodes to traverse upward. Node 1's parent reference is updated to point to previous, which is node 2, completing its reconfiguration. We also ensure there are no lingering child references by setting node 1.left and node 1.right to none. Finally, we update previous to node 1 and terminate the process as current is now none. The tree transformation is complete, and the final tree is rooted at node 3, with node 2 as its left child and node 1 as the left child of node 2. Now, we examine a tree that includes both left and right children. The input tree has node 1 as the root, with node 2 and node 3 as its left and right children respectively. Node 2 itself has a left child, node 4. The goal is to make node 4 the new root. We initialize current at the leaf, node 4, and set previous to none. In the first iteration, current is node 4, which has node 2 as its parent. We save node 2 as next underscore node, set current.parent to previous, and remove all child references from node 4. This isolates node 4 from its original position. Then, we rewire node 4 to point to its parent, node 2, by setting node 4.left to next underscore node. We update previous to node 4 and move current to node 2. In the second iteration, current is now node 2, with node 1 as its parent. We save node 1 as next underscore node, reconfigure node 2's parent to point to previous, node 4, and clear all child references from node 2. At this point, node 2 is isolated from its original position. We then rewire node 2 to point back to its parent, node 1, by setting node 2.left to next underscore node. After updating previous to node 2, we move current to node 1. In the third iteration, current is node 1, which no longer has a parent. We save next underscore node as none, reconfigure node 1's parent to point to previous, node 2, and remove any remaining child references. With previous updated to node 1, and current set to none, the process ends. The tree is now rooted at node 4, with node 2 as its left child and node 1 as the left child of node 2. Finally, we consider the simplest case, a tree with just a single node. The input tree consists of node 1, which serves as both the root and the leaf. Here, since there are no other nodes to traverse, current starts at node 1, and previous is set to none. In the first and only iteration, node 1 has no parent, so next underscore node is saved as none. We simply set node 1.parent to previous, which is none, and there are no child references to remove. After updating previous to node 1 and setting current to none, the process concludes. The tree remains unchanged, rooted at node 1. Overall, this algorithm efficiently reverses the tree structure by traversing from the leaf to the root, carefully rewiring parent-child relationships while severing unnecessary links. The result is a valid tree rooted at the specified leaf node. The time complexity of the flip binary tree function is determined by the height of the binary tree, denoted as h. This is because the algorithm processes the tree from the given leaf node back to the root, modifying the connections along the way. First, let's consider the traversal. The algorithm moves upward through the tree using the parent pointer, and in the worst-case scenario, this involves visiting every node along the path from the leaf to the root. For a balanced binary tree, the height h is proportional to log n, where n is the total number of nodes. However, in the case of a degenerate tree, which is similar to a linked list, the height becomes proportional to n. Next, we examine the rewiring operations. At each node, the process involves constant time pointer updates, such as modifying the left, right, and parent pointers. These operations are O(1) for each node. Since every node along the path is visited just once, the total time spent on rewiring is directly proportional to the height h of the tree. With that in mind, the total time complexity of the algorithm is O(h), where h is the height of the tree. For a skew tree, which is the worst case, the height h equals the number of nodes n, and the complexity becomes O(n). On the other hand, for a balanced tree, the height h is proportional to log n, making the complexity O log n. Now let's turn to space complexity. The algorithm has a space complexity of O(1), because all operations are performed in place without requiring auxiliary data structures. First, since the algorithm is iterative, it avoids the overhead of recursion, meaning that no extra space is used for function calls. Second, the rewiring operations, which involve updates to the parent, left, and right pointers of nodes, are performed directly in the tree without allocating additional memory. Additionally, the algorithm uses only a constant number of variables, such as current, previous, and next underscore node, all of which occupy O1 space. Combining these points, the total space complexity remains O1 in all cases, as no extra memory is allocated. Let's compare this to a naive approach. A less efficient method might involve reconstructing the tree from scratch. This would require O(n) time to traverse all the nodes and additional O(n) space to store the new structure, making it significantly less efficient. In contrast, the current solution is optimized in both time and space. By leveraging the parent pointer and performing in-place rewiring, the algorithm avoids the need for extra space or a full traversal of the entire tree, making it far more efficient. Now let's analyze the best, average, and worst-case scenarios. In the best case, for a balanced tree, the height h is proportional to log n, resulting in a time complexity of O log n. For the average case, most binary trees have a height closer to log n, so the time complexity remains O log n. However, in the worst case, such as a skewed tree, the height h equals the total number of nodes n, leading to a time complexity of O(n). The mathematical reasoning for this big O complexity lies in the fact that the traversal from the leaf to the root dominates the runtime, and this traversal is proportional to the height h of the tree. Since each rewiring operation at a node is O(1), the overall time complexity becomes O(h). As for space complexity, it remains O(1) across all cases because the algorithm does not require additional memory and modifies the tree in place. When solving this problem, there are a few common mistakes to watch out for. First, not handling edge cases properly can lead to issues. For example, if the input node is already the root, or if the tree contains only a single node, failing to account for these scenarios might cause null pointer exceptions or incorrect results. Another frequent mistake is incorrectly reversing the parent-child relationships. While rerouting edges, it's easy to overwrite the reference to the original child before properly reassigning its parent. To avoid this, make sure to store temporary references during the reversal process. Additionally, when making the given node the new root, don't forget to update its parent pointer to null. Missing this step could accidentally create a cyclic structure in the tree. Finally, inefficient traversal is another pitfall. Some solutions unnecessarily traverse the entire tree to locate the target node, which can result in O(n) complexity, even if the target is located much closer to the root. Optimizing the traversal can help avoid this inefficiency. Another common variation to watch for is misunderstanding the problem constraints. Remember, the input is a binary tree, not a binary search tree. Assuming node placement follows binary search tree rules can lead to incorrect results. From an interview perspective, this problem tests several important skills. First, mastery of tree traversal is essential. You should be comfortable with recursion and iterative methods, as well as understanding how parent-child relationships work in binary trees. Additionally, understanding the data structure is key. Trees with parent pointers differ from traditional binary trees, and recognizing these differences will help you navigate the problem. Edge case handling is another area interviewers often focus on. Be prepared to discuss scenarios like when the target node is already the root or when the tree is minimal. Lastly, be ready to analyze trade-offs. For example, recursive approaches may be more intuitive, but they come with the risk of stack overflow, whereas iterative methods require more careful pointer management. This problem also connects to several related problems that can help deepen your understanding of binary tree manipulation. For instance, in LeetCode 1.14, Flatten Binary Tree to Linked List, you restructure a binary tree, which shares similarities with this problem. Another relevant problem is LeetCode 1.05, Construct Binary Tree from Preorder and Innerorder Traversal, which focuses on reconstructing trees based on parent-child relationships. Additionally, LeetCode 2.36, Lowest Common Ancestor of a Binary Tree, is useful for understanding traversal and parent tracking in binary trees. Finally, LeetCode 16.50, Lowest Common Ancestor of a Binary Tree 3, is particularly relevant since it also involves trees with parent pointers, which require a similar understanding of how to navigate and modify tree structures. There are several alternative approaches you can use to solve this problem, each with its own advantages and trade-offs. The recursive approach involves reversing the parent-child relationship while traversing up the tree. This method offers clear and concise logic but comes with the risk of stack overflow, especially for deeply nested trees. On the other hand, the iterative approach uses a while loop to reverse the relationships. While this method avoids the risk of stack overflow, it requires careful handling of temporary pointers to ensure correctness. Another option is the path storage approach, where you store the path from the root to the target node and then reverse the relationships along this path. This method simplifies the edge reversal logic but comes at the cost of additional space to store the path. Choosing the right approach depends on the constraints of the problem and the trade-offs you are willing to make in terms of space and complexity. Great job! In summary, we solved the problem by restructuring the binary tree using traversal techniques. We discussed the time and space complexities, along with some key takeaways. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!